All right, so last time we just got that real general introduction to the linear mixed model. Let's start out this part of the screencast lecture by just remembering why are things so different when we consider an effect to be fixed rather than random. Okay, so I know we talked about this last time, but just for review, fixed effects are the treatments and they don't change. They are the same. If you replicate that experiment, the treatment levels are going to be the same, and we would be studying those same treatments in the same way. Versus when we have random effects, we can think of these as a random sample from a population of potential treatments. So teachers in a classroom, they're out of the whole population of all teachers. Books from a library, out of a whole population of all books, and so forth. If we run the experiment, we're looking for an entirely new sample of treatments. So for example, if I've done a lexical analysis paper on, and if I had redone that experiment, I would not have selected the same books that we did for our lexical analysis models. We would have selected a different subset out of the population of books. Inference is on our population of potential treatments. So we don't want them to be too specifically focused. Like we didn't want to say, oh, the dragons from mountain A are really different than the mountains from dragon B. We don't care about that. What we care about is the overall amount of heterogeneity contributed by where the dragons come from. Okay, so we would want to use random effects in cases like this. Use this as your rule of thumb, and then I have my really simple, easy rule of thumb that I'll let you in on. That usually works for me pretty darn well. So here's the 3 things to think about. Number 1, we actually have sampled treatments from a population. So this is a really good indicator. You're going to need random effects. If you just have some teachers from a school or from a district, you need a random effect for teachers. If you just have some organisms from a population of organisms, random effect. Treatments are supposed to represent a population of treatments about which we want to know more about. So those treatment levels are from a bigger group, and we want to know and infer upon that bigger group from which we have not sampled the entire group. It's not exhaustive. 3, sampling patterns in the collection of the units have induced some sort of similarities or correlations or dependencies among our units that we can model. And the random effects in our model help us model them particularly. So again, students in the classroom is a classic way to think about it. Students within one class are going to behave kind of similarly versus students in another class, even if they have similar characteristics like gender, socioeconomic status, academic background, and so forth. We'll see some similarities just because of the fact they have the same teacher and are in the same classroom environment. That last point's really important because random effects are a model for that variability. Remember, that's how we talked about it in class. We were talking about the percentage of variation contributed by that random effect that we get from that intercluster correlation. That's what we're really focused on. It looks like we're affecting the mean, but we're not. We're actually affecting that random variation or covariance. We can get a lot more complicated than just one random effect. It can be crossed, nested, multiple. It can get pretty wild, okay? Now, when I look at a study and I'm trying to figure out if things should be fixed or if things should be random, in that experiment, I think a very simple thing, and it's very similar to point number 1 on the previous slide, which is if I were to do this experiment again, would I get those same levels of treatments? If my answer is yes, then I make it fixed almost all the time. If my answer is no, then I make it random almost all the time. It's a really good dividing rule, and if it's not clear to you, you just need to think some more about your design and how you're selecting your treatment levels and so forth. If you can't give an easy answer to that, then you don't know your setting well enough at that point. Okay, one more way. When we have fixed effects versus random effects, here's another difference. Fixed effects, hierarchical models are our default with some weird exceptions here and there. With random effects, non-hierarchical models are really reasonable, and in most cases are the most reasonable. And in fact, I kind of test different models, some with hierarchy, some without hierarchy, in terms of the random effects only, to see which one fits better when I build random effects models. The fixed effects, if you have a mixed model, meaning it includes both fixed and random effects, you still want to keep those hierarchical. Maybe there would be some, I'd need to think through if that's absolute, especially if you have a random slope where your fixed effect varies according to the level of some random factor, then that could get a little dicey. But we'll talk about that later. We haven't gotten to those models yet. So this issue of hierarchy is really different for random versus fixed. Fork in the road. That's a really pretty picture, isn't it? I wonder, I forget where he is, Minnesota. But this is a fork in the road. We have to decide when we have a treatment, are we going to go off in the random direction? Or are we going off in the fixed direction? Oh, and I see. I thought I couldn't remember what he was referring to here. Here we're doing old school versus new school, and I made reference to the old school approach in class last time and showed you my old school calculations. This is how I was taught to do it. It's certainly how Gary was taught to do it. I'm going to emphasize new school with you guys, okay? The textbook emphasizes old school. In the old school, what you do is you compute an ANOVA table for your random effects model as if it were fixed. Then you fix what needs to be fixed and make sense of the random effects setting. For simple cases, the old school is easy and it works pretty well, but for more complicated cases, especially if we have crossed or nested random effects, it's really hard or can give you really weird things like negative estimates for variance. It happens all the time. I can show you some data. It's happened to me personally when I was in graduate school. Getting negative estimates for your variances is a no-go, and the only solution when I was taught this stuff was to set it to 0 when you got a negative estimator, which seems like a horrible solution to me. The new school is the Rimmel approach, restricted maximum likelihood estimation. I'm going to give you a handout that we'll go over in class. This is actually Gary's handout that we'll use. It's not easy. I actually evaluated some kind of slight modifications to the Rimmel method for my master's research, and it's not super easy to understand, but it's easy to implement. You just run it in R. The theory behind it is a little bit more difficult though. Then this is better for handling the more complicated cases that we will see. It also will not give you a negative estimator for your variance ever, which is great. We will see some cases where the old school and new school approach agree and some cases where they don't. But I'm quickly going to quit even looking at old school. I don't even know why I bring it up anymore, to tell you the truth. So let's kind of go over the basics. I know you've all had maximum likelihood estimation in your stat 5380. You would have had it there. That's where I've taught it, I know. Probability density for a normal looks like that. This is our bell curve distribution. If we have end results, it's the product of the individual densities that are independent. Key, independence, then we can allow those to be the joint distribution of y1 up to yn is just the product of the marginal distributions of yi. And then we can adapt this for more complex mean structures like a regression or factorial, or more complicated variance structures like the random effects. But this is the basic thing you really need to understand, which is easy, thank goodness. Then you turn this around and you look at this like a likelihood function. So here it is written as a likelihood function. If we take the natural log of this, it's going to be converted to this, and this is typically what we use to derive theoretically those maximum likelihood estimators, like in stat 5380. You've done this a million times, I'm sure. So those maximum likelihood estimates of the parameters are those parameters that make that data the most likely and give that highest value for that likelihood function. MLEs we know have a lot of great properties, and especially when we look at the asymptotics at large samples. We know from calculus that if we maximize and take the derivative of that log likelihood function with respect to both mu and sigma squared, and set the derivatives to 0, we solve for those parameter values and we get the following. You've done, like I said, you've done this. I remember doing this my first semester in graduate school. I don't think I ever did it as an undergrad, but in graduate school certainly, and far more complicated, right, than this. Note that the divisor in the estimated variance is n and not the n minus 1 that is unbiased. This n shows up for regression factorials and so on. In mixed effects, we need to remember that it includes both fixed and random. We have the fixed part, the random part, and then the error. Mixed effects are called mixed effects because it's both. The fixed effects can be anything we've talked about up until this. It can have qualitative factors, it can have the polynomial terms, any of the above. I've built many with polynomial and random effects, very reasonable. Random effects part can be real general, but we're going to just talk about terms that are additive in the random effects. I'll probably mention and show you some that are not, that are multiplicative in particular. The parameters that we get from this model here, the mixed effects model, is going to be the usual fixed effects parameters, but also the variance for that random effect. So last time in class, we just did a random effects model. So all we got was a reported variance having to do with that factor that was our random effect in the model. Now we'll get that variance for the random effect, our MSE, the error residual variance, as well as fixed effects parameters when it's mixed. One of the problems with the usual MLE is sigma squared's tendency to be underestimated. And so this gets us to kind of a fix that we will use in this class. I'll address that in the next set of notes.